Hello everyone, and welcome. I'm excited to have you here today. Today, we're going to explore the fascinating world of servo motors. Our presentation is titled, Servo Motors Explained, and we'll be diving into how they work, their applications, and why they're so important in automation. Over the next few slides, we'll cover the basics, some technical details, and real-world examples to give you a clear understanding. So, let's get started and discover the power behind precise motion control. Now, let's take a quick look at what we'll be covering today. Our agenda starts with an introduction to servo motors, where we'll explore what they are and why they're so important in automation and robotics. Then, we'll dive into how servo motors actually work, breaking down the mechanics and control principles behind them. Next, we'll discuss how to choose the right servo motor for your specific needs, considering factors like torque, speed, and precision. After that, we'll look at various applications, highlighting the versatility of servo motors across different industries. We'll also cover how to interface servo motors with microcontrollers, which is essential for building intelligent systems. Finally, we'll touch on some advanced topics for those interested in pushing the boundaries of servo motor technology. Throughout the presentation, we'll see how these concepts connect to the bigger picture of designing efficient and precise automated systems. Now, let's dive into the basics of servo motors. These devices are essential in many automation and robotics applications because they provide precise control of position, speed, and torque. Unlike regular motors, servo motors are designed to respond accurately to control signals, making them ideal for tasks that require high precision. They typically consist of a DC motor, a gear train, and a feedback device, such as an encoder, which constantly monitors the motor's position. This feedback loop allows the servo to adjust its movement in real time, ensuring accurate positioning. Understanding how servo motors operate is fundamental because they are the building blocks for creating complex, automated systems that need reliable and precise movement. Throughout this presentation, we'll see how these motors integrate into larger systems and why they are so vital in modern automation. A servo motor is essentially a type of rotary or linear actuator that provides highly precise control over position, whether that's angular or linear. It's designed to accurately control how fast it moves and how far it goes, which is crucial in many applications. At its core, a servo combines a motor with a sensor that constantly feeds back information about its position, allowing for real-time adjustments. The main components of a servo motor include the motor itself, a feedback device, like a potentiometer or encoder, that keeps track of the position, a control circuit that processes signals, and a gear system that amplifies torque and ensures smooth motion. These parts work seamlessly together to deliver that precise control we rely on in complex systems. You'll find servos everywhere, from robotics and CNC machines to remote-controlled cars and airplanes, because of their ability to deliver reliable, accurate movements. Understanding their components and functions helps us appreciate how they enable the advanced, precise automation that's shaping our world today. Now, moving beyond rotational movement, let's talk about linear servos. These are designed to provide straight-line motion, which is especially useful in applications like controlling valves or in systems that require precise positioning. Instead of spinning around, they push or pull directly in a straight line, making them ideal for tasks that need accurate linear control. Next, let's focus on the most common type, the linear servo. These typically operate within a range of about 0 to 180 degrees, much like a standard rotary servo, but their movement is linear rather than rotational. You'll find them widely used in hobby projects and small-scale robotics because they are straightforward to set up and reliable for many applications. Then there are the positional rotation servos, often called wheel servos. These can rotate continuously, similar to a regular DC motor, but with the added ability to control their position. This means they can spin indefinitely, which makes them perfect for driving wheels or creating continuous motion systems. Connecting all these points to the overall theme, understanding the different types of servos, whether linear, positional, or continuous rotation, helps us choose the right motor for the specific motion control needed in our projects. Each type offers unique advantages depending on the application's requirements. Let's talk about some of the key advantages of using servos. One of the biggest benefits is their precise control. They can position themselves very accurately, which is essential in automation tasks where exact movements are critical. Additionally, servos offer a high torque-to-size ratio, meaning they can deliver a lot of power relative to their small size, making them ideal for compact designs. They're also fairly easy to interface with microcontrollers, so integrating them into your projects is usually straightforward. Because of their precision and reliability, servos are often the go-to choice when accuracy really matters. Now, on the flip side, there are some disadvantages to consider. Servos tend to be more expensive than standard motors, which can add up, especially if you're working on a larger project or multiple units. They also require more complex control systems to operate effectively, which might mean additional circuitry or programming complexity. And let's not forget about power consumption. Servos can draw a significant amount of current, which can be a concern, particularly in battery-powered applications where conserving energy is important. So, while servos bring a lot to the table in terms of control and precision, it's important to weigh these advantages against the potential costs and design complexities. Understanding these trade-offs helps us choose the right motor for each specific application, aligning with the overall goal of creating efficient, reliable automation systems. Now, let's take a closer look at how servo motors actually work. At their core, servo motors are designed to precisely control angular position, velocity, and acceleration. They do this through a feedback loop, which is really the secret to their accuracy. When you send a command, the motor doesn't just spin aimlessly. It actively measures its position using a sensor, typically an encoder. This sensor constantly feeds information back to the control system. The control system then compares the actual position with the desired position, and if there's any difference, it adjusts the power sent to the motor to correct it. This closed-loop system allows servo motors to make very fine movements and hold positions steadily, even under load. Think of it like a smart navigation system, constantly checking where you are, where you want to be, and making all the necessary adjustments to get you there smoothly. This precise control is what makes servo motors ideal for robotics, automation, and any application where accuracy is critical. So, in the grand scheme of automation and robotics, understanding how servo motors work helps us appreciate their role in enabling precise, reliable movement. They're not just simple motors. They're intelligent, feedback-driven systems that keep everything aligned and functioning smoothly. Now, let's take a closer look at the motor itself. The motor is essentially the heart of the servo system, providing the actual power needed to move the servo to the desired position. When selecting a motor, we typically consider types like DC motors, AC motors, and brushless DC motors, each offering different performance characteristics. For example, DC motors are simple and easy to control, while brushless DC motors tend to be more efficient and durable. The choice depends on what the application demands. Next, we have the feedback system. This part is crucial because it measures where the servo shaft actually is. Common devices include potentiometers and encoders. Potentiometers are simple and cost-effective, but encoders provide much higher precision, which is important for tasks requiring exact positioning. The feedback data is sent back to the control circuit, allowing the system to know how close it is to the target position at any given moment. Speaking of the control circuit, this is the brain behind the operation. It continuously compares the position you want the servo to be in with the actual position it's in right now. Based on that comparison, it adjusts the motor's speed and direction to correct any error. Many systems use PID controllers for this task. These help fine-tune the adjustments, making the movement smooth and accurate. Finally, the internal mechanism ties everything together. It translates the motor's movement into the actual rotation or positioning of the servo arm. This mechanism is designed to ensure precise and reliable motion, which is essential for the overall performance of the servo. Together, these components form a smart, responsive system that allows us to achieve precise control over movement. something that's fundamental across countless robotic and automation applications. Now, most servo motors are controlled using a technique called pulse width modulation, or PWM signals. The key idea here is that the width of the pulse sent to the servo determines its position. So, in simple terms, by changing how long the pulse lasts, we can control where the servo points. Typically, these pulses range from about 1 millisecond to 2 milliseconds. The servo interprets these pulse widths to figure out the desired angle or position. It's like giving the servo a set of instructions on how far to turn, based on how wide that pulse is. And of course, the microcontroller, whether it's an Arduino, Raspberry Pi, or another device, sends these PWM signals to the servo. This means that controlling the servo becomes quite straightforward because the microcontroller handles generating the signals required. So the main takeaway here is that the microcontroller acts as the control hub, sending precise PWM signals that tell the servo exactly where to move. This connection between the microcontroller and the servo is what makes automation and robotics so versatile and responsive. Now let's talk about power requirements, which are really fundamental for ensuring your servos work smoothly. Typically, servos operate on low voltage, around 5 or 6 volts, which makes them compatible with many common power supplies. But what's just as important is the current they draw. This depends on the load. They'll need more current when they're working harder or under heavier loads. So, choosing the right power supply isn't just about matching the voltage. It's about making sure it can deliver enough current to meet the demands of all your servos. This leads us to the key point of power supply selection. You want to make sure your power supply can handle the total current draw of all your servos, plus a little extra safety margin. Why is that important? Well, if the power supply isn't capable of providing enough current, you might see erratic servo behavior, like jittering or stalling, which can really disrupt your project. So always plan for a bit more capacity than you think you'll need. It's better to be safe than sorry. Ultimately, selecting the right power supply is crucial for reliable operation and smooth performance, tying back to our overall goal of building a dependable and efficient robotic system. Now let's move on to slide 11, which is all about selecting the right servo. Choosing the appropriate servo is a critical step because it directly impacts the performance and reliability of your project. First, you'll want to consider the load requirements, how much weight or force the servo needs to handle. This helps you determine the torque specifications you need to look for. Next, think about speed. How quickly does the servo need to respond? Faster responses are often necessary for precise control, but they might come at a higher cost or power consumption. Another key factor is precision. How accurately does the servo need to position itself? Different applications demand different levels of accuracy, so understanding your specific needs here is essential. Also, consider the size and mounting options, making sure the servo fits within your design constraints and is easy to install. Lastly, don't forget about durability and environmental conditions. Will the servo be exposed to dust, moisture, or extreme temperatures? Choosing a servo rated for those conditions can save you from future headaches. Overall, selecting the right servo isn't just about picking the most powerful or the fastest one. It's about aligning the servo's capabilities with your project's specific demands. When you do that, you'll ensure smooth operation, longevity, and optimal performance, which ties back to our overall goal of building efficient, reliable systems. Let's talk about servo torque specifications. The datasheets for servos specify something called stall torque, which is essentially the maximum torque the servo can exert before it stalls or stops moving. It's really important to keep in mind that your actual load torque should be well below this stall torque to prevent overloading the servo and risking damage. Now, torque is all about rotational force, and you'll often see it measured in units like kilogram-centimeters or ounce-inches. When selecting a servo, you want to make sure it can handle the load you expect it to move. To estimate the load torque, think about the weight your servo needs to move, the distance from the pivot point, because torque increases with distance and any acceleration involved. And I always recommend overestimating your load torque rather than underestimating it. That way, you ensure your servo has enough power and there's a safety margin built in. So, understanding these torque requirements and how to estimate load torque is key to choosing the right servo for your project and making sure everything operates smoothly and reliably. Let's take a closer look at speed ratings for servos. When we talk about servo speed, it's usually measured in seconds per 60 degrees of movement. This means if a servo has a speed of, say, 0.2 seconds per 60 degrees, it takes that amount of time to rotate through that angle. Choosing a servo with the right speed is crucial because you want it to meet the demands of your specific application. Faster isn't always better if it doesn't deliver enough torque, but too slow might not be responsive enough for your needs. Now, an important point to keep in mind is balancing speed and torque. There's often a trade-off here. Generally, as the speed of a servo increases, its torque tends to decrease, and vice versa. So when you're selecting a servo, think about what's more critical for your project. Do you need quick, rapid movements, or do you need high force to hold or move heavier loads? Finding that sweet spot between speed and torque ensures your system performs optimally without sacrificing reliability. Ultimately, understanding your speed requirements helps you make smarter choices. Whether you need fast response times or strong holding power, aligning your servo's capabilities with your project needs is key. Remember, the goal is to choose a servo that strikes the right balance, delivering enough speed while providing the torque necessary for your application to operate smoothly and efficiently. When selecting a servo, it's important to consider its operating temperature range. Some applications might expose the servo to extreme temperatures, so choosing a model that can handle those conditions is crucial for reliable performance. If the environment is particularly hot or cold, make sure the servo you pick is rated for those temperatures. Additionally, environmental factors like moisture and dust can really impact the servo's operation. If your project involves exposure to water, humidity, or dusty conditions, you'll want to go for a sealed or waterproof servo. This helps protect the internal components and ensures the servo continues to operate smoothly over time. Overall, paying attention to these environmental considerations, temperature, moisture, and dust, helps us select the right servo for the job, which is key to building a robust and dependable system. Now, let's explore the various applications of servo motors and see how they play a crucial role across different industries. First, you'll notice that servo motors are widely used in robotics. They provide precise control of movement, which is essential for robotic arms and autonomous vehicles. Next, in manufacturing automation, servo motors are the backbone of CNC machines and conveyor systems, ensuring accurate positioning and smooth operation. You'll also find them in aerospace applications, where their precision helps in controlling flight surfaces and other critical components. In the consumer electronics arena, servo motors enable functions like camera autofocus and drone stabilization, improving performance and user experience. Additionally, in medical equipment, they allow for delicate and precise movements, such as in surgical robots or imaging devices. The key point here is that regardless of the industry, the common thread is the need for accurate, reliable, and efficient motion control, something servo motors excel at. Connecting this back to our overall theme, these applications highlight just how versatile and vital servo motors are in advancing technology and automation in our daily lives. Now, let's take a closer look at how servo motors are utilized across different aspects of robotics. First, in robot arms, servos play a crucial role in controlling each joint's position and movement. Their high precision ensures that the robot can perform tasks accurately and repeatably, which is essential in everything from manufacturing to delicate assembly work. Moving on to bipedal robots, servos are vital for maintaining balance and coordinating gait. They allow these robots to walk, run, and even perform complex maneuvers by adjusting their joints in real time. It's a fascinating application of precise control that mimics human movement. Finally, in autonomous vehicles, servos are used to manage systems like steering, brakes, and other mechanical functions. This precise control is what enables these vehicles to navigate safely and smoothly, responding dynamically to their environment. Overall, whether it's a robotic arm, a walking robot, or an autonomous car, servos provide the accuracy and responsiveness needed to bring these machines to life. They're a fundamental component that helps bridge the gap between mechanical systems and intelligent, autonomous operation. Let's take a closer look at CNC machinery and how servo motors play a vital role in their operation. The key here is precise positioning. CNC machines depend heavily on servo motors to control the movement of their cutting tools with remarkable accuracy. This level of precision is essential because it directly impacts the quality of the parts being produced, ensuring they meet exact specifications and standards. Now, moving on to multi-axis control, this is where things get really interesting. Servo motors enable CNC machines to operate across multiple axes, which means they can create complex shapes and intricate designs that would be impossible with simpler machines. This multi-axis capability opens up a world of possibilities for manufacturing detailed and sophisticated components. When we connect these points, it's clear how critical servo motors are in enhancing the flexibility, accuracy, and complexity achievable with modern CNC machinery. This all ties back to our overarching goal of improving manufacturing precision and efficiency through advanced automation technology. Now, let's talk about how servos are used in various remote-controlled vehicles. In RC cars, planes, and boats, servos are essential for controlling steering and throttle. They respond quickly and accurately to our commands, giving us precise control over the movement and speed of our models. This responsiveness is what makes these vehicles so fun and realistic to operate. Moving on to camera gimbals, servos play a crucial role here as well. They help stabilize the camera, ensuring that footage remains smooth and steady, even when the vehicle is bouncing or experiencing turbulence. This stabilization is key for capturing high-quality video, especially in dynamic environments. Overall, whether it's guiding a car around a track or capturing breathtaking aerial footage, servos are the backbone of control and stability in remote-controlled vehicles. They enable us to achieve both precision movement and smooth operation, which is really at the heart of what makes these models so exciting and versatile. Now let's move on to slide 19, which focuses on interfacing with microcontrollers. This is a crucial aspect because, as we've seen, microcontrollers are the brain of many embedded systems. To effectively communicate with them, we need to understand the key points involved. First, there are different types of interfaces, such as digital and analog, each serving specific purposes. Digital interfaces, like UART, SPI, and I2C, are commonly used for communication between microcontrollers and peripherals. It's important to choose the right one based on factors like speed, complexity, and number of devices. Next, we have to consider voltage levels and signal integrity. Ensuring that the signals are compatible and free from noise is vital for reliable communication. Sometimes, we need level shifters or buffers to match different voltage standards. Another key point is the importance of proper wiring and grounding to prevent issues like signal interference or data corruption. Connecting this to the overall theme, effective interfacing ensures that our microcontroller-based systems operate smoothly and reliably. It's not just about connecting wires. It's about understanding the protocols and electrical characteristics to optimize performance. So, mastering these interfacing techniques is fundamental for designing robust embedded systems that can communicate seamlessly with sensors, actuators, and other devices. Now, on this slide, we're looking at the Servo library that comes with the Arduino IDE. This library is a real game changer because it makes controlling servo motors much simpler. Instead of manually generating PWM signals, which can be a bit tricky, the library handles all of that behind the scenes for us. It automatically manages the PWM signal generation, so we can focus on what we want the servo to do rather than how to generate the signals. What's really neat is that with just a few lines of simple code, you can control the position of a servo by specifying an angle. The library takes care of translating that angle into the appropriate PWM signal, so you don't have to do that math yourself. This mapping process is quite efficient and makes programming servos more accessible, especially for beginners. Overall, the key point here is that the servo library streamlines the process, making it easier to integrate servo motors into your projects. This fits perfectly with our overall theme of simplifying robotics and automation tasks. So, whether you're building a robotic arm or an automated camera, using this library can save you a lot of time and effort. Now, let's talk about the GPIO pins on the Raspberry Pi. These pins are incredibly versatile because they can generate PWM signals, which are essential for controlling servos. But, as you might imagine, this requires some careful timing and proper configuration to get it just right. Moving on, to make controlling these GPIO pins easier, we often turn to Python libraries like RPi, GPIO. These libraries simplify the process, allowing us to easily interface with our servo motors without getting bogged down in the low-level details. And of course, all of this ties back to the core theme of making hardware control accessible and manageable through programming. The combination of the GPIO pins, capabilities, and the power of Python libraries really opens up a lot of possibilities for our projects. Let's talk about troubleshooting issues with your servo. If your servo isn't responding at all, the first thing to check is the power supply. Make sure it's providing the correct voltage and current needed. Next, verify all wiring connections. Loose or faulty wires can cause communication problems. Also, check the control signals. Ensure your microcontroller is sending the right PWM signals, because incorrect signals can lead to no response. Now, moving on to jittering, which is when the servo moves erratically or vibrates unintentionally. This often happens due to electrical noise or an unstable power source. To fix this, one effective solution is adding a capacitor across the power supply lines. This capacitor helps smooth out voltage fluctuations, providing a more stable power flow. Both of these issues, non-responsiveness and jittering, highlight the importance of proper power management and reliable connections. Troubleshooting these common problems ensures your servo operates smoothly, which is crucial for achieving precise control in your projects. Remember, addressing these points helps keep your entire system functioning reliably and efficiently. Now, let's move on to some advanced topics that really deepen our understanding of this subject. These areas are a bit more complex, but they are essential for anyone looking to master the material. First, we'll explore some key concepts that build on the foundational ideas we've discussed so far. These include more sophisticated techniques and emerging trends that can give us a competitive edge. As we go through these, I want you to think about how they connect to the overall theme of innovation and continuous improvement. These advanced topics aren't just theoretical. They have practical applications that can transform how we approach challenges and opportunities in our field. By understanding these concepts thoroughly, you'll be better equipped to adapt and implement strategies that lead to better outcomes. So, let's dive into these advanced ideas and see how they can elevate your knowledge and skills. Now, let's talk about feedback control and the importance of tuning the PID parameters. When we refer to KP, Chi, and CADE, we're talking about the proportional, integral, and derivative gains. These are the key settings that determine how well our control system responds. Adjusting these parameters is really crucial if we want our system to perform optimally. Achieving that optimal performance usually requires some experimentation and iterative tweaking. It's not just about setting numbers and forgetting about them. It's about observing how the system reacts and refining those values to get the desired response. Implementing a PID control algorithm can really make a difference. It helps improve servo performance by reducing overshoot. That's when the system exceeds the target, and by minimizing the settling time, meaning how quickly it stabilizes after a disturbance. Overall, tuning these parameters effectively is central to making our control systems both responsive and stable. It ties back to our broader goal of achieving precise and reliable control in our applications. Now, let's take a closer look at brushless servo motors. These motors are known for offering higher efficiency, which means they convert more electrical energy into mechanical work, reducing waste and saving energy. They also tend to have a longer lifespan because they generate less heat and experience less wear over time compared to traditional brushed motors. Plus, their performance is generally better, providing smoother operation and more precise control. These qualities make brushless servo motors especially ideal for demanding applications where reliability and high performance are crucial. You'll often find them in high-end robotics, where precision and durability are essential. They are also widely used in aerospace, where safety and dependability are non-negotiable, and in industrial automation, where consistent, high-quality operation is a must. So, in the context of our overall discussion, these motors exemplify how advanced technology can meet the rigorous demands of modern industries, ensuring both efficiency and longevity in critical applications. Looking ahead, let's talk about some exciting future trends in smart servos. One key development is the integration of microcontrollers and sensors directly into the servo itself. This means the servo can now perform advanced functions like self-diagnostics and adaptive control, making systems more autonomous and responsive. Essentially, these smart servos are becoming smarter and more self-sufficient, which opens up a lot of possibilities for complex applications. Another major trend is the use of AI algorithms to enhance servo performance. By leveraging AI, we can optimize how the servos operate, ensuring they adapt to changing conditions in real time. This leads to systems that are not only more efficient, but also more reliable over time. Connecting these ideas back to our overall theme, it's clear that the integration of intelligent features and AI is transforming traditional servos into highly adaptable, self-aware components. This evolution is paving the way for more advanced robotics and automation solutions in the future. As we come to the conclusion, I want to take a moment to highlight the key points we've discussed. Throughout this presentation, we've explored how implementing effective strategies can truly transform our approach and outcomes. We've seen the importance of embracing innovation, fostering collaboration, and maintaining a focus on continuous improvement. These concepts are all interconnected and essential to driving success in our field. Remember, the overall theme is about adapting to change and leveraging opportunities to stay ahead. So, as you move forward, keep these ideas in mind. They're the foundation for sustainable growth and progress. Thank you for your attention, and I look forward to seeing how you apply these insights. Now, let's take a closer look at servo motor essentials. Servo motors are highly precise actuators that are used across a wide variety of applications. Their ability to deliver accurate position, speed, and torque makes them indispensable in many fields. Understanding the different types of servo motors, how they work, and the various control methods is crucial for anyone looking to use them effectively. Moving on to their applications, you'll find servo motors everywhere, from robotics, where they enable precise movement and manipulation, to CNC machinery, where they control cutting tools with remarkable accuracy. They are the backbone of systems that require controlled and repeatable motion. To tie this all together, the key points highlight that mastering servo motors involves knowing their types, mechanisms, and control techniques. This foundational knowledge allows engineers and technicians to optimize their use, ensuring high performance in their projects. Ultimately, these concepts are integral to the broader theme of automation and precision engineering, helping us build smarter, more efficient systems. So, looking ahead, the future of servo technology is incredibly promising. We're seeing ongoing advancements that will make these systems more efficient, more reliable, and smarter than ever before. This means we can expect servo solutions that not only perform better, but also adapt more seamlessly to the needs of different industries. One of the most exciting developments is the integration of artificial intelligence and intelligent features. These innovations will enable servo systems to learn from their environment, optimize their performance in real time, and even predict maintenance needs before issues arise. Overall, continuous innovation in this field is going to open up new possibilities and drive the next wave of automation and precision. It's an exciting time, as these advancements will help us create smarter, more responsive, and more capable systems across a wide range of applications. Thank you so much for watching. I really appreciate your time and attention. I hope this presentation has given you a clear understanding of the key ideas we've discussed. Remember, the main takeaway is how these concepts connect to the bigger picture, whether it's improving processes, driving innovation, or enhancing teamwork. It's all about applying what you've learned to make a real difference. If you have any questions later on or want to dive deeper into any topic, don't hesitate to reach out. Thanks again for being such an engaged audience. I look forward to seeing how you put these ideas into action.